Given the title of this study, I would like to emphasize that we want to approach this problem from a system perspective. That is to see the whole phenomena of delay propagation from a global perspective, because generally this problem has been addressed taking into account an airport or a few airports. But we believe it is important to consider all direct and indirect relationships of all system components. In other words, consider all the elements of this complex network that is the air traffic network. Briefly, the outline will start with the motivation, or why is it important to understand this problem. Then I will describe the database that we use to develop this work. Then I will define the network and the dynamic cluster to visualize this system congestion. And I will show you some preliminary data results. And then I will go directly and define the model that we use to analyze what is happening here and compare some results obtained from the model and compare it with what has actually happened on the system. Up to this point, we are going to understand the delay propagation phenomena only taking into account internal mechanism or endogenous causes to the system. And from this point onwards, I will show you what is the effect of a large-scale external disruption on the system. This means what happened when there is a weather perturbation that affects and modifies the system. Okay, I would like to emphasize that beyond the economical or practical consequences that understanding this problem may provide, the main interest, at least for me, is the peculiarities of the delay propagation dynamics. Unlike other studies on transport network, in which, for example, packets of information are broadcasted following a particular protocol, in our case, we must add that these packets have to meet a calendar or a schedule. So this makes us pay special attention to the evolution of the dynamics. And also, this could be a good example of how an error an error could propagate through the system and later on involve all the system. In this case, the delay will magnify throughout the day. I just want to point out that we are not interested in primary delay. Of course, there's always a first cause to delay a plane. That could be weather or mechanical failure in an aircraft, but the main interest is analyzing how this first delay spreads and eventually magnifies throughout the day. This is what we call, or this is called the reactionary delay, and is what we want to understand. Such delay, the reactionary delay, may occur because the aircraft rotation throughout the day, and also because as a flight they have to wait for connecting passenger or flight crew from another flight on, or because an airport gets congested and later on we congest all the departing flight from it. As you can see in these charts, this one is in Europe, the share of delay in minutes when comparing reactionary delay to primary delay, reactionary delay is almost half for 2010 and 2011. And in the US, if we don't have this division of primary and reactionary delay, but you can see that only taking into account that reactionary delay is aircraft arriving late, this amounts for 41% of the total causes of delay. But of course, as I told you before, reactionary delay is not only aircraft arriving late. It is also the flight connectivity and the airport congestion. Okay, so to develop this work, we use the airline on-time performance database that is publicly available at the Bureau of Transport Statistics of the US. And for each flight of this database, we have the schedule and the actual departure and arrival times. Also, of course, we have the origin and destination airports, the airline ID, or which company does the flight belong to, and the aircraft code or tail number. This last datum is crucial because it allows us to reconstruct the itinerary of each aircraft throughout the day and later on reconstruct the schedule of a whole airline, and so reconstruct the schedule of the whole system for a day, for a particular day. For the year under analysis, that is 2010, we have more than 6.5 million flights on the database. That is, this accounts for the 74% of the total US domestic flights for that year. This involves 18 carriers, the major US carriers, and that connect 305 airports on the network. These numbers could vary from day to day, but it's close to what I show you here. As you may imagine, the network is defined by the airports that are the nodes, and the edges are defined as direct flight between these airports. Also in this picture, the nodes have certain attributes as the average delay per flight, and in this case, the size of the node means the average delay per flight. So the larger is the node, the longer is the delay on that airport. Also, the color means the degree of each node. For instance, here Atlanta has an intense color because it's a network hub and has many connections to other airports on the network. Okay. Define the network, we have to define the cluster that we use, the dynamic cluster that we use to visualize this system congestion. So we did this by defining cluster as a group of airports that their average delay per flight of each airport is higher than 29 minutes, and also the second condition is that they must be connected. This is, at least, is really important, this second condition. And to be connected means that there must be at least one flight route between them. So you can see in this figure that we have two clusters, cluster A larger and cluster B, and cluster A is larger than cluster B. So from now on, the color codes will be red for the largest cluster in a period of time. This could be, in some cases, the whole day or an hour of the day. And then in yellow, there are other clusters that are in the system, but they do not belong to the larger cluster in a certain time period. And in green, of course, airports that doesn't have any problem at all. So then, what we did is we ran all the days of 2010 according to the daily departure delay, and we divide the best days and the worst day of the year. Here we can see that the best day according to the daily departure delay was April 19, and we will show you the result for this day. And also, the second worst day of 2010 was March 12. As I told you on the introduction, here we consider for the first part of the presentation, I will consider this day, March 12, and not October 27, because we are interested in understanding the causes of delay propagation, but only the internal causes, that is, the endogenous causes to the system. And in October 27, that we will see afterwards, there was a major storm complex that affected the Mideast part of the United States. So this will be at the final part of this presentation. Okay, here we can see how it looks, the map or the network, the air traffic network of the United States. For instance, for the best day of the year, you can see that the largest cluster is only 2 airports located in these states. Here what we have is an intermediate day that is not one of the best days, nor one of the worst day of the year, and you can see how it starts to appear some cluster, but they are all in yellow, only the largest cluster here in Alaska. They are all in yellow because they didn't merge and form a large cluster on the network. And here are the results for a congested day. And you can see that there is a large cluster, mainly located at the East Coast, and some airports at the West Coast of the United States. Okay, from these maps, you can see that there is a great variability from comparing day to day. And this is confirmed when we take the largest cluster size for each day of the year. You can see how there is a great variability from day to day. And this means that consecutive days are very different to one another. Also, this variability is not only comparing day to day, but if we see within a same day, and we see the evolution. And we see the evolution of the cluster throughout a day. We can see how, yes, we can see how it starts to appear sporadically in different parts of the network. Some airports that are congested, and then if you wait until 10 a.m., you can see how when Atlanta gets congested, it will start propagating this delay throughout the network. You have to wait until 10 a.m. Here it gets congested Atlanta and start propagating to the neighbors of the neighbors, and we will see how this starts rising and reaches the maximum size. I think it's at 5 p.m. or 4 p.m. and then it will start to diminish, this large cluster. Of course, here the node size is the average delay for each airport, and you can see now how it will start to diminish, and will eventually it will disappear, this congestion, this system congestion. Okay. So this variability is not only taking into account the size of the clusters, but also we can ask, for instance, and we can answer the question if all the airports if the airports are always the same. The airports that are in problem are always the same. And we do this by computing the Jaccard index. And for instance, if the Jaccard index has a value of 1, it means that the airports in one cluster are the same when comparing the other cluster. And although we can see here in this figure that some comparing consecutive days, some have a Jaccard value of 1, the vast majority have a low Jaccard value. This means that when comparing consecutive days, the airports in problems are not always the same. And also, if we take into account, if we compare the ranking, that is the worst day of the year, compared to the second worst and so on, we can see also that the Jaccard index has a low value. And also, of course, comparing the base days. So this also shows a great variability, and of course consecutive days are very different each other, not only from the size of the cluster, but also the airports comprising the largest cluster of the day. Okay, so in order to analyze how this dynamic is generated and evolves, we develop an agent-based model in which agents are more the 4,000, roughly the 4,000 aircraft that are part of the system every day. And also the model is data-driven because we need the actual schedule or the real schedule to take into account and to analyze this problem. This model has 3 internal mechanisms, that is flight rotation, flight connectivity, and airport congestion. For flight rotation, what I mean is that, for instance, if a plane wants to go from Palma to Tenerife through Malaga and it gets delayed in Palma, probably it will get delayed the next flight leg from Malaga to Tenerife. This if the ground time in Malaga is not sufficient to absorb the delay. In this internal mechanism, we take into account the real schedule and a minimum service time that is for ground operation. This means, for example, embarking, disembarking, refueling, etc. The second mechanism considers the connection between flights of the same airline. Through this process, a flight may be delayed because it has to wait for passenger or crew, mainly crew, from another flight of the same company. As we have no information of which flight is connection of which other, we do this process, we randomly select the connection. We do this, for instance, if we have the schedule departure for a certain flight of, I don't know, American Airlines, and we see 3 hours prior to the scheduled departure of this flight, and we see all the scheduled arrivals of American Airlines that are in this that belongs to this time window. And then from all these possible connections, we select the ones that, for instance, we take a random number between 0 and 1, and if this is higher than the flight connectivity parameter alpha that we define here, and the airport plus and the airport connectivity, this is what we call a connection of this flight. So this flight will have to wait for this connection to arrive to the airport in order to depart. Here is the airport connectivity. That this means that certain airports, for instance, I don't know, Chicago, is a hub for Delta Airlines. So it means that many people use Chicago as a connection, as a connecting airport to fly, for instance, I don't know, from the West Coast to the East Coast, and so on. And also, in this model, only by fitting this parameter, because we have two parameters, beta and alpha, only by fitting this parameter, we can match what we see on reality. The third mechanism is airport congestion, and this means that all the airports have finite capacity. This capacity is measured at the scheduled airport arrival rate, and as you can see this figure, this capacity, or the scheduled airport, or the scheduled rate, is varied throughout the day, and it's very different for each airport. So this mechanism means that, for instance, if the real rate of arrival to a certain airport is higher than the scheduled airport arrival rate, a queue will start to form in that airport. So aircraft in that queue will have to wait the aircraft being served by this. Will have to wait for this time of the other airports in order to get served and then depart. Also, we have the capacity parameter here that we use in many of the in all the simulation we use this beta equal to 1. That this means that we use the nominal capacity of each airport. And finally, the initial condition, we use the initial condition taken exactly from the data, because we know when, where, and the departure delay of the first flight of the sequence. And also we can take random initial condition. That this means, for instance, that we have a fixed initial delay in minutes and a percentage of initially delayed planes that we use. Okay, just for visualization purposes, what I will show you here is a video of how this model works. Here we have a flight delay from Syracuse, that is an airport there, to Atlanta, and it's delayed. And we will see this is how all the connections get delayed, because it has to wait for this first flight, and later on this will propagate throughout the network. Of course, here we use an alpha parameter and realistic alpha parameter that we use 0.5 when the normal value is 0.2 for a congested day, and we use this value only for visualization purposes. Okay, so let's compare the data results with the model. So these are the 2 days that I told you before: an uncongested day, and a congested one, the best day of the year. And you can first you can see the big difference between the behaviors of the evolution of the cluster size throughout the day for a congested day and a congested one. And this still remains for other days that are congested. In a congested day, you can see a shaped curve, and well, in the best day, you cannot see anything or any pattern, because it's only, in this case, for instance, it's only the largest cluster size, it's only 2 airports. And also, we did this for all the days of the year, and we find good agreement between the model and what we see in reality. Also, another point that is interesting to analyze is the evolution of the number of clusters per hour, and it follows that, for instance, for a congested day, it's always the same. There is a large number of clusters at the beginning of the day, and then it starts decreasing throughout the day, this number. And you can interpret this as, for instance, there are many clusters located in the system, and then from this time, for instance, onwards, they will start merging to form a large cluster in all the system. And also, if you can see in the decaying phase, there is no, it never happens that you have a more number of clusters, for instance, a peak here, and this means that in the decaying phase, at least you can interpret as that the largest cluster will dissolve continuously, that the cluster doesn't pull apart one another. And for instance, yes?
Up to 8 a.m., where are the points of data?
Sorry? Here. They are the same.
They are the same?
Yes.
Exactly?
Exactly.
And the same on the view on the right?
And the same? Yes. Because in this case, you have we use the real first initially delayed flights. So that makes sense to have the same points in the model and in the data. For at least the first flights of the aircraft rotation. Okay. So also in a good day, you can see that you don't have this pattern, this diminishing pattern in the number of clusters. And also, the second question that we want to answer is which of the internal mechanisms is more important to propagate this delay. So to do so, we can turn off and turn on the different mechanisms. For instance, in this case, what we did is we turn off the flight connectivity, and we assume that the airport have infinite capacity, and you can see how only with plane rotation the model is not able to reproduce this system congestion or this large congestion in the system. In this case, only taking into account that airports have finite capacity, so we turn off the flight connectivity, the answer is also negative. Only with this internal mechanism we cannot match what we see in reality. But only taking the connectivity of flights and assuming that the airports have infinite capacity, we can match, the model can match what we observe in reality.
But isn't this then kind of unphysical then? If you assume conditions which are not the reality and then it fits the data?
Mm-hmm. Well, you mean, for instance?
But you say they have infinite capacity.
Yes.
In the middle.
This one.
Yes. What are the parameters again here in the middle graph?
In the middle graph, if we use beta, it's like infinite in this case, yeah. And alpha, it was like 0.2 or something like that. But it's not that the airport congestion is not important, because the airport congestion, as we see it, or at least I see it as a way of introducing new primary delay. That later on, this will get magnified by this mechanism. We'll see afterwards in a few. Okay, another question or issue that we want to address is the system resilience. And to do so, we evaluate or we see the system output, in this case the largest cluster size, according to the initial input that we give to the system. This initial input, as I told you, is a fixed value of initial delay and a fraction of initially delayed flights. So, comparing through the columns, that is, comparing the 2 days, we can see how here in March 12, the congested day, this transition from a free flow regime to a congested one starts earlier according to this initial input. And also, if we compare the two rows, this is by diminishing the flight connectivity parameter, we can see how this surface congestion decreases as well. So this is another way of validating that, in this case, flight connectivity is a key factor for the rise of the congestion in the network. And also, you can see from this graph that the model output depends on the initial conditions. So, in some sense, this model is sensitive to the initial condition that we give to the model. So, okay, up to now, we analyze what happened only taking into account internal mechanisms to the system. But what about October 27, that it was a day that it was disturbed by weather perturbations? So what we did is we saw and we searched in the internet what happened this day. And this day, what happened was that there was a major storm in the Mideast part of the United States, and high winds, etc. And what we see in the news that it affected JFK, mainly JFK, LaGuardia, and Newark. And also we cross-checked this information from the news with the National Weather Database, and we see what was the events taking place on October 27. Okay, so the first thing that we did is using the basic model that I explained before. Only with this model we can reproduce what we see on the data, and the answer is negative, as you can see here in the green curve, and the data, that is this one, the red. You can see how neither the growing phase or the decaying phase match what we see in reality. So for weather perturbed days, we have to include this external perturbation into the model, and also the external interventions into the model. That this means the flight cancellation policies. So in order to do so, we translate this external perturbation, this weather perturbation, into the model by affecting the airport capacity, that is this beta parameter. So in this case, what we did is we diminish this beta for, well, here is wrong, we did it only for JFK, LaGuardia, and Newark. We diminish this beta parameter value to 0 between 8 a.m. and 10 a.m. Eastern Time. And you can see in this case how the growing phase match, for instance, what we see, or closely match what we see in reality. But then we have the decaying phase that we still have this problem that it doesn't match. And why is that? This is because we have to model the external interventions into the system. And this external intervention, by this external intervention, I mean, for instance, flight cancellation policies. Because when you have a congested day, for instance, airlines or the people on the Federal Aviation Agency start cancelling flights, and this, of course, will affect the propagation of the delays. So to do so, we take 3 variants. In variant number 1, what we did is and we interpret this flight cancellation policy by a decrease on the alpha connectivity of on the alpha connectivity parameter. So on variant number 1, what we did is we decreased this flight connectivity to 0 between 7 p.m. and 9 p.m. the maximum when this congestion reaches the peak, the maximum. And we see how this the decreasing phase start to match, but not really good, what we see on reality. In variant number 2, what we did is, let's see the sensitivity to the decrease on the value of the alpha parameter. And we see that if we drop not to 0, but 50% of the actual value, because the value for the basic model was 0.26, what we see is that there is no big difference between when we change the value from a 100% decrease or a 50%. But in variant number 3, what we did is, we dropped this flight connectivity parameter to half the value, but we make this time window when we apply these flight cancellation policies larger. So this one was from 7 p.m. to 9 p.m. also here, but here we put it from 6 p.m. to 10 p.m. And we can see how this improves the declining phase. Okay. So from here we can conclude that it makes sense to interpret cancellation policies as a decrease on the network connectivity, on the whole network connectivity, and there is a higher sensitivity to the size of the time period that we apply this decrease on the flight connectivity parameter. Okay. Also, we want to address this issue and see what is the effect of the schedule on the delay propagation phenomenon. To do so, we use for comparison purposes the schedule of October 20. This was a week before, and for this day it showed a low congestion because actually the largest cluster for October 20 was only 2 airports on the whole system. And also, you can see from this figure the cancelled flights for October 27 and October 20, and you can see that there's an abnormal rate for October 27, the highly perturbed day because of weather disruption, as to compare with this, the cancelled flights for October 20. So, summarizing, what we did is we used the initial condition of October 27 and we put it on the schedule of October 20 to see what happened. And what happened is that if we analyze the evolution of the cluster size, this is using the schedule of October 20 and using the initial condition of October 27. So what we conclude from this is that the schedule of October 27 was not the main reason for the unfolding of the delays, the actual schedule, because it's a modified schedule, it's not the prior schedule of the day, and that, of course, the real intervention measures taken on October 27, because when people realized that they will have a huge congestion in the network, were a palliative to the delay spreading mechanisms. Okay, so in summary, we have defined a new way of measuring the network-wide spread of the delay, and we find that there was a strong variability between days and intraday, and also we introduced and we developed a model to analyze, for instance, the resilience of the system, and we found that there was a non-negligible risk of system instability, and we think that this could be translated to other transport modes if this transport mode, of course, have a schedule to implement. And in the final part, I show you a way of mimicking the external perturbations to the system. And in this case, what we saw is that the external perturbation could be modeled as a decrease in certain airport capacity parameters, and the external intervention, the flight cancellation policies, could be modeled as a decrease in the network connectivity. If you are interested in further work, these are the articles that we did until now, and I want to show you some of the ongoing work that we are trying to do. What we are trying to do is to analyze the susceptibility of the system to the input that we give to it. For instance, what we want to see is if we only delay only one flight, not many flights as is the normal case in the system, if we only delay one flight, if this can trigger a delay propagation throughout the network. So, of course, with only one flight to trigger a delay propagation that affects the whole system, we have to increase the flight connectivity parameter, because the normal value for congested days is around 0.2, but in these cases that we only want to analyze what happens if we delay one flight, we use an alpha value of 0.5. And for instance, this depends on many things. It depends on the time of the day, because what we did here is, okay, we delay an initial flight that goes from a certain airport to Atlanta, and we see, according to the value that we give to this initial flight, the value of delay if this can trigger a congestion on the network. And we see, for instance, if this flight arrived at 4 a.m. or if this flight arrived at 5 a.m., what will happen? And we see that there's no congestion on the network. But if this flight arrived at 6 a.m., we can see that if the value is higher than 150 minutes of the delay, it can trigger a congestion that involves at least, for instance, 45 airports on the total system. And if we go on, in this case, we have a congestion, but in this case, so-so. And this, because it depends not only which airport you are affecting, but the airline that flight belongs to. And in this case, maybe the airline was a small airline according to the number of scheduled flights, and you can see how this doesn't trigger a huge congestion over the network. But for instance, in this case, at 8 a.m., what we see is that there is a transition from a free flow regime to a congested one around 100 minutes, and this will continue throughout the day. But of course, if you delay a plane that arrives at Atlanta at 10 a.m. or 11 a.m. or 12 p.m., there's no time, because this is a time constrained system. It will not have time to develop this large congestion over the network. And you will see that, of course, if the arriving plane arrives at Atlanta at 5 p.m., there will be no time to develop this congestion. But the problem with this is that we have more than 4,000 flights initially to get delayed, so computationally this is too hard to do. So what we are trying to do now is not looking at the edges, or not looking at the flights on the network, but looking at the airport. So what we will do is to perturb an airport or delay an airport and decrease the beta parameter of that airport, and we will see what happens. And that is a computational feasible problem. So that's all. Thank you very much.
So, thanks, Pablo. Questions?
So the connectivity that you mentioned, this alpha parameter, this is something that you compute, or it's something that you take from the data?
No, it's something to modulate what we think that would be the flight connectivity.
But this put by hand?
Yes,
or,
exactly.
okay.
Yes.
So you have to guess more or less
Yes.
which value is the...
To see, to match what we have on reality, to match what we see on the data, we fit this alpha parameter.
So it's a fitting
Yes,
parameter.
it's a fitting parameter. But not the beta, because the beta we use the nominal capacity. Not when we have to model the external interventions, but when we want to understand, only taking into account the internal mechanisms of the system.
I'm just curious about the distribution of time delays.
Yes.
Have you checked the...
Yes, it's a broad. You mean it's a broad tail. You have a broad tail there, because you can have flights delayed. What we saw in the data, you can have flight delays almost like 18 hours or something like that. And this is taking into account the delays for flights. But if you account for the delays of person, this is much higher, because if you miss a plane or a connection, you can stay at the airport, I don't know, 1 day or whatever the airline wants to put it.
So 18 hours is a cut to consider that they consider that distance?
We don't know. We don't know what is the airline policy. But we saw in the data. I don't know how airlines compute that, but we saw in the data flights delayed 18 hours or something like that.
I was wondering in your model, your flight connectivity, is there a maximum time for the flight to wait for passengers coming from another?
In the model,
Yeah.
no, we put it like
So you can wait 8
Yes.
hours for the passengers?
exactly.
That's not realistic.
But yeah, it's unrealistic. But that affects the alpha parameter value, because if as you say, if the flight, it's not for passengers, but mainly for flight people. But if the flight has to wait many hours, and in reality, what the airline does is to cut, for instance, if it's delayed 45 minutes, it will cut and won't wait for the flight. This information, the way I see it, is put inside the value of the alpha parameter. So in that case, the value will be diminished, because all that information is put in when you want to fit the system, what you see on the real. I don't know if I was clear. But
I mean, a similar question is for what you draw on the table there. Do you have also a sort of a minimum time that you cannot select the flight right before the following one?
yes, we use 3 hours.
Well, but I mean, you could select the one that is very close to the next departure.
This one?
Yeah.
Yes.
Because I guess you need also
No,
some time
yes,
to build
exactly.
the plane and whatever.
No, we took that into account.
Ah, you took that.
Yes.
Yes.
We put like 30 minutes, something like that, or
Okay.
to this transit time. Or,
Yeah.
yes.
So the total cost per year was something about 40 billion.
41 billion.
What is the relative cost compared to, let's say, what they are gaining, or the total cash flow of the airlines?
Yes. Well, I used to have that numbers on my head, but I can look after.
Well,
Okay. We can talk.
More questions? Marina?
Can you get data for when France went down?
For
When France was down?
Air France.
No, for France, when the air traffic, when they're on strike in France for the traffic. And they have to.
That's a big problem because it's Europe.
It's Europe.
So in Europe we don't have. Well, this was supposed to do it with European data, but of course European data is too much. It's much harder to obtain, so we don't have, because of, I don't know, privacy or copyright issues. The Eurocontrol doesn't give us the data.
If you look at the volcano also, without talking about the French strike.
So I mean, the US, there is a law that they forced to give the data, make it public in the US, and so we can get all that. But in Europe, it's impossible. So it's not public, and even if you ask inside, the project are hard to do.
Exactly.
So we don't have access.
There's no law to enforce the airlines to give the data to, for instance, to do this type of thing. But it's not sensitive data, it's only data. I don't know why they don't want to give us.
It's very clear, because you could look which is the airline that has a large
Yes.
number of delays and just
Yeah,
But
But
that is
popular. The airlines claim that this is the airline which is more on time than any other
But
airline.
the same argument applies to the US. And they are
But that is good to the people because we have more information to decide.
Yeah, you are using most often the cluster size of the size of the connected component of the airports. Would it not be more maybe relevant to use another measure, like there's a total number of delayed airports not necessarily connected? Why is relevant that they are connected and no?
Because at the first place we wanted to understand this. It's not a causal effect, but we want to understand this spatio-temporal correlation between airports. So this gives us an idea of if there is a certain relationship in this sense with the propagation that is from one airport to the other. And I don't know if, okay, you can see it by the number of airports, but we want to see it also if this airport could affect the neighbors and so on. And this, we see it only if we take into account that they are connected. If not, there's no a priori, or there's no relationship between.
Yeah, so I'm going to see what mechanism is important and what is not. Maybe some mechanism is not important for having a large connected component of delay airports, but it does give you a lot of airports with delay.
No, exactly.
If it is the case, then it's also bad. No?
Yes, but we saw, if that was the case, for instance, for instance, in April 19, there was a good day, we saw if, okay, the largest cluster was only 2 airports, but in some cases, we also saw if there were other airports not connected, and this, well, at least we didn't saw that you can have the situation that the larger cluster is small, but you have many disconnected clusters. We didn't see that kind of results.
Your analysis of I think it was the 27th of October, when you changed the time window where you had the disruption. So this more or less says that it's a feature of the connectivity of the network, no?
This?
Yeah, because basically the start and the build-up of the cluster size is the same for all the conditions. It only changes in the end, so
yes.
In other words, it takes the network, depending on when the disruption takes place, it takes longer to get rid of the effects.
Yes.
So at some point, do you think you will be able to say how to modify certain structures to spread out its effect and make it less pronounced? Or
well, that would be really good to do that kind of stuff. I don't know. We can, for instance, in this case,
maybe it's just changing 2-3 connections between 2-3 networks to guide it around. So
exactly. Maybe if you only modify, not here, what we did is we modified all the network connectivity, and we didn't see if maybe the problem are only these airports, but maybe only decreasing the connectivity between these airports and the rest or the neighbor. Maybe we have a more effective way of diminishing the network congestion. And there is, for instance, in the United States, there is a ground delay program that the FAA, what it do, for instance, it says there is a ground delay program, for instance, for Atlanta. So all flights arriving to Atlanta will get delayed, and so that's a way of diminishing the pressure in Atlanta. Yeah. And also, in this next step, when we analyze the susceptibility, we can see that kind of stuff. If we issue a ground delay program for Atlanta, we can see what happened on the rest of the network.
More? If I can make a last question. So this is a system that has to handle external and internal perturbations, right? You have airlines, you have control and all that. So typically, one of the solutions to these problems in natural basically solved by criticality, right? So placing the system close to a critical point, right? This is one of the solutions. Well, this is an engineer system, so there is somebody taking decisions, right? So this is not self-organized, it's really controlled. So my question is, because it's not clear to me, do you think that this is working somehow or has signatures of criticality despite being an engineer system or not? What do you think about that?
Well, intuitively, maybe yes, because as you say, this is done by people, so people take decisions, but there are many decisions and many different people taking. For instance, you have many different airlines. That it's not that there is a big brother taking the decisions over the network, and in that sense, maybe.
But there is not somebody, because in nature what happens is that the bad solutions are removed from the system, right?
Yeah.
In nature the bad solutions are removed. This is a way to select and to really have some kind of self-organization, right? So here it's not clear to me whether there is such a thing, but the bad solutions are really
we can
sanctioned, punished.
We can try to see if that happens.
So, thanks a lot.
Iba a poner, pero después
Es un sistema pero es natural.
Bueno, es lo que estoy preguntando, Juan. Bueno, eso es lo único. ¿Cómo estoy dando el caso? No sé, no es lo que tendría que cada vez mejor, pero no me el plan existe una presión suficientemente fuerte. Y por eso se me dice que nadie puede seleccionar.
¿Qué hacemos? Si te va a ir un vuelo, se le dice habitualmente, ese vuelo se retrasa con cierta periodicidad.
Eso ha pasado aquí con muchas compañías, porque al final tampoco tiene, no hay tantas opciones, hay 2 o 3. Con lo cual,
cogiendo siempre el vuelo por la mañana.
entonces sí, sí puede ser, pero no lo tengo muy claro. Y además las curvas que muestra, que finalmente tampoco ninguna firma muy clara de que haya leyes de potencia, pues sí. La distribución de los retrasos es muy ancha, pues tampoco, sí.
Es monótono.
Bueno, la miramos acumulada, porque si no puede ser, sí. Pero no es monótona, supongo que si miras. Pues ocurren cosas raras, por ejemplo, vuelos que están 18 horas retrasados. Pero claro, esos son convenios que entiendo. Hay convenios. Luego tienes el problema, por ejemplo, de la noche. Si tienes un vuelo retrasado por la noche y lo retrasas hasta el día siguiente porque está cerrado el aeropuerto, ya sumas el sol. Tienes cosas de estas que no son fáciles de sumar. Tienes una mezcla, tienes mezclas de estas cosas y así. Pero bueno, en general, bueno, la pregunta esta del sistema autoorganizado no lo tengo muy claro.
Sí, no.
Eso creo que tendría que ser. Porque si una torre de control, quiero decir, no tiene ninguna presión para mejorar, los que están allí, bueno.
No, los que tienen el poder de estos son las compañías de decir, cancelo estos vuelos de las 8 y las...
Claro, pero el tráfico se controla independientemente. Tienes las compañías aéreas que te dicen los vuelos, pero tienes la torre de control y luego lo controla en Europa que te dice pasa o no pasa. Y entonces no lo tengo muy claro. Y luego además como hay cada país, es un conglomerado en Europa que es un conglomerado...
O sea, aquí hay 2 cosas. Una es la evolución de la red hasta llegar a donde está.